Now, carbon monoxide. Carbon monoxide reacts with steam. This is H2O gas to produce carbon dioxide and hydrogen. At 700 Kelvin, we don't need a comma there, at 700 Kelvin, the EQ constant, equilibrium constant, is 5.10. Calculate the EQ concentrations of all species if 1.000 mole of each component, each component means each species, is mixed in a 1.0 liter flask. Okay, our reaction is, they said, carbon monoxide gas plus steam, which is H2O gas, forms carbon dioxide gas plus hydrogen gas. So that's our reaction. And it is balanced, so it's 1, 1, 1, 1, not a problem. Okay, so let's read this. Carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At 700 Kelvin, the equilibrium constant is 5.10. So we have our, let me do this in blue now, it's 5.10. Calculate the equilibrium concentrations of all species if 1.0 mole of each of the components, and that means 1 mole of each, is mixed in a 1 liter flask. Okay, now the first thing we need to do is we're going to, and again, this is sort of something we're always going to do. This is the procedure. We're going to write the equation, which we have. We're going to write the equilibrium expression, and then we're going to check the reaction quotient to see where the reaction is at that moment to see which direction is actually going to be moving in. So let's write the equilibrium expression for this, which is going to be the same as the reaction quotient. It is the concentration of H2 times the concentration of CO2 divided by the concentration of CO times the concentration of water. Okay? And that's also equal to the reaction quotient. So the first thing we want to do is calculate the reaction quotient to see which direction it's moving in. Now they say they put in 1.000 mole of each component. Well, it's sitting in a 1.0 liter flask, so basically I can work with moles. 1 mole divided by 1 liter is 1 mole per liter, so the concentration of each species is 1 mole per liter. Well, so now let's calculate the Q. The Q equals, well, it's 1 molar of the H2, 1 molar of the CO2 divided by 1 molar of the CO and 1 molar of the H2O. The Q equals 1. Now the reaction quotient Q, which is equal to 1, is less than 5.10. Remember, they gave us the 5.10, which is equal to K. When Q is less than K, that means the reaction wants to move forward to produce more product in order to reach equilibrium. That means it hasn't reached equilibrium yet. It is still moving forward. It is producing more product to reach equilibrium. That means carbon monoxide and H2O gas are being depleted. And for each amount that these are depleted, because the ratio is 1 to 1, an equal amount of CO2 and H2 are being formed. Now we can do the actual equilibrium part of this problem. So again, these 1 molar, that came from where we started at that moment. At any given moment, boom, I stick in 1 mole of each in a 1 liter flask, and let me find out what this value is. It's 1, it's less than the equilibrium constant. That means it's going to move forward to the right. Okay. So now let's do our equilibrium part, and we do that by doing our ice chart. So let me rewrite CO plus H2O. I tend to tend to rewrite things a lot. Sorry about that. Hope it's not a problem. I'm sure you have different ways of doing it yourself, as long as each of these is here. So it goes to CO2 plus H2. Okay, we have an initial concentration, we have the change, and we have our equilibrium concentrations, which is what we're looking for. Our initial concentrations are 1.000, right? That's how much we started with. We stuck each of those in a flask. Now, this reaction quotient tells us that the reaction is moving in that direction to reach equilibrium. It's moving in that direction. That means CO is disappearing. H2O is also disappearing by an amount X. That means a certain amount is decomposing. A certain amount of CO is being lost, is being converted. Well, since it's moving to the right, and this is 1 to 1 to 1 to 1, that means this is plus X. That means CO2 is forming for every 1 mole of this that's disappearing. So this is also plus X. I hope that makes sense. So our equilibrium concentration, at equilibrium, once everything has stopped, a certain amount of CO has been used up. So our equilibrium concentration is going to be 1.00 minus X. A certain amount of H2O has been used up. That's 1.000 minus X. A certain amount of CO2 is formed. So it's going to be 1 plus X. And a certain amount of H2 is formed. 1 plus X. These are our equilibrium. Oh, wow, that's interesting. Look at that. Yes. Let's get these lines out of the way. This is our equilibrium expression, but notice now we have X, so we need to actually find X. Fortunately, we can do that. We can plug it into the equilibrium expression, right? Because the equilibrium expression is a measure of these concentrations at equilibrium. That's what these values are. We stick it in here. We know what the KEQ is. It's 5.10, and we solve for X. That's it. It's just an algebra problem. So let's go ahead and do that. So K, which is equal to 1.000 plus X times 1.000 plus X. That's the CO2 and H2 concentrations, divided by the CO and H2O concentrations, which at equilibrium is 1.000 minus X, 1.000 minus X, and we know that that equals 5.10. Okay, so now let's just handle this algebraically. This is 1.000 plus X squared over 1.000, oops, too many zeros, 0 minus X squared equals 5.10. Now, I know that I said earlier, I think a lesson or two ago, when you're writing out the equilibrium expression, don't square it immediately if two of the things are the same. That's different than what I'm doing now. I wrote the expression as each species separately so that I can see that I actually have 4 species in my equilibrium expression. Here, now I'm just dealing with the math. Once you've actually written it out, then you can go ahead and write it like this to deal with the math. Now it's 1 plus X squared over 1 minus X squared. That's fine. But when you initially write the expression, don't cut corners. Write down everything. We want to know that the expression actually consists of 4 terms, not 2 terms each squared. Okay. And now we just, well, we have a square here and a square here, so we'll just go ahead and take the square root of both sides, and we end up with 1 plus X over 1 minus X equals 2.258, 2.258, and then we multiply through to get 1.000 plus X equals 2.258 minus 2.258 times X. I'm hoping to God that I'm doing my math right here. So we end up with 3.258x equals 1.258, and x is equal to 0.386 molar. So we found x. X is 0.386 molar. Now if you go back to your ice chart, it didn't ask for what X was, it asks for the final concentration. Well, the final concentrations were the 1 minus X and the 1 plus X for those 4 species. So the CO concentration, carbon monoxide concentration, which also equals the H2O concentration, is equal to 1.000 minus X, 1.000 minus 0.386 equals 0.613 molar. So the carbon monoxide and the water are at 0.613 molarity. Now the CO2 concentration, which also happens to equal the H2 concentration, is equal to, okay, let's see if we can clean this up a little bit. We're not going to have these straight lines driving us crazy all day. CO2, I just really need to learn to write slower, I know that that's what it is, equals H2 concentration equals 0.000 plus X equals 1.000 plus 0.386, 1.386 molarity. Okay, and my friends, we have done it.